Good afternoon, sir. Myself J. Tabassum. My roll number is 234C1A04B5. I am from Electronics and Communication Department. In this video presentation, I am going to explain about a topic from the subject Control and Systems, subject code 23EE404. In control systems, I am going to explain about a topic called state variable and a state model. Introduction to state variables. State variables are essential for describing the state of a system. They represent the minimum set of variables needed to predict future states. Understanding state variables is crucial for system analysis and control design. Definition of state variable. A state variable is a quantity that represents the state of a system at a given time. It can be physical quantity like position or velocity, or abstract like temperature. State variables provide a complete description of a system in a given context. Importance in dynamic systems. State variables are fundamental in the study of dynamic systems. They allow for the formulation of system equations that govern behavior over time. This information is critical for control engineering and system design. Example of state variables. Common examples include position, velocity, acceleration, and temperature. In economics, state variables can represent resources, capital, or inventory levels. Each example reflects key aspects of systems behavior over time. State space representation. State space representation involves modeling a system using state variables. The state of a system is represented as a vector in a multidimensional space. This technique allows for a unified approach to analyze different types of systems. State equations. The state equations describe how the state of a system evolves over time. They are typically expressed in first-order differential difference equation. Understanding these equations is important for predicting future behavior. Input and output variables. Input variables are external factors that influence the system state. Output variables are the measurable quantities that result from the system's behavior. Together, these variables define the relationship between the system's inputs and outputs. Linear versus non-linear systems. Linear systems have state equations that are linear function of state variables. Non-linear systems have equations that include non-linear relationships. The complexity of the state model increases significantly in the non-linear cases. Time invariance versus time variance. Time invariant systems have state equations that do not change over time. Time variant systems have equations that evolve with time, affecting predictions. The distinction is crucial for selecting appropriate analytical techniques. Stability in state models. Stability refers to the system's ability to return to equilibrium after a disturbance. It is assessed using criteria based on state variables and system equations. Understanding stability is essential for designing robust systems. Controllability and observability. Controllability indicates whether we can drive the system to a desired state. Observability measures whether the internal state can be inferred from outputs. Both concepts are fundamental for effective system control and monitoring. Designing state feedback controllers. State feedback controllers use state variables to adjust system inputs. This design enhances system performance by stabilizing or optimizing behavior. The controller's designs relies heavily on the state space representation. State estimation techniques. State estimation is used when state variables can't be directly measured. Techniques such as Kalman filter helps estimate states from noisy measurements. Accurate state estimation is critical for effective system control. Applications in engineering. State variables and models are widely used in mechanical and electrical engineering. They help in designing systems like robotics, automation, and aerospace. These applications rely on accurate modeling for performance and safety. Application in economics. In economics, state variables can represent capital accumulation and resource allocation. State models helps to predict economic trends and assess policy impacts. This application highlights the versatility of state variable concepts. Simulation of state models. Simulation is a powerful tool for analyzing state models. It allows for visualizing system behavior under various conditions. Simulations help in validating control strategies and system designs. Challenges in state modeling. One challenge is accurately capturing the dynamics of complex systems. Nonlinearities and time variant behavior complicate the modeling process. Addressing these challenges requires advanced analytical and computational techniques. Future trends in state modeling. Advances in machine learning are influencing state model development. Data driven approaches are emerging for more accurate state estimation. Future trends may include integration with IoT and real time analytics. Conclusion. State variables and models are foundational in understanding system dynamics. They provide critical insights for control, estimation, and optimization. As technology evolves, their importance in various fields will only increase. Thank you.